Hello, friends, and welcome to yet another lecture on chemical engineering thermodynamics. Today, we will be studying how to solve a problem on isothermal reversible processes. The fluid is an ideal gas. The problem is on your screen. 1 kilomole of an ideal gas occupies a volume of 4 meter cube at 600 kilopascals. It is compressed isothermally to 2 meter cube. Compare the heat supply. Calculate the heat supplied and the work done. Also find the change in internal energy and enthalpy. The first thing that we need to understand here is that U, internal energy, is a function of temperature for an ideal gas. Therefore, in any process, if the initial temperature is equal to the final temperature, then the initial internal energy is equal to the final internal energy. Therefore, the change in internal energy is equal to 0. So for an isothermal process, the change in internal energy will be 0. A similar logic can be applied and it can be told that change in enthalpy is also equal to 0. That is because enthalpy is defined as U plus PV for any fluid, and U is a function of temperature for an ideal gas, plus PV for an ideal gas can be written as nRT. Now, as you can see here, that T ends up being only a function of temperature. Therefore, change in enthalpy is also 0. Now, how do we calculate the heat and work? We can, of course, commit the formulas to our memory, or we can do it the way I'm demonstrating it, where we need not commit things to memory and solve it logically and get our answers. So we apply the first law to the system. Now, moles given is 1 kilomole, and this does not change during the process. Therefore, it's a closed system. If we have to visualize this process, it is done as follows. Y-axis is the pressure, x-axis is the volume. This is the initial pressure and this is the final pressure. Now what do we have? Initially it is at 600 kilopascals and its volume is 2 meter cube. Sorry, let me correct it. 4 meter cube. It is compressed reversibly till its volume is 2 meter cube. So the process is along this red line, where this is state 1 and this is state 2. The temperature is held constant. So let's find out the final pressure and the temperature for the gas to ease our calculations. Now what do we have is, with the ideal gas law, we can write PV is equal to nRT. Now we know that the pressure is 600 kilopascals and the volume is 4 meter cube. The mass of gas is 1 kilomole. R is 8.314 kilojoule per kmol. K Kelvin, and T is the temperature. Therefore, we get the temperature as, let's calculate it out, 600 multiplied by 4, and let's divide it by 8.314, and we get it as 288.669. 288.669 kelvins. Now that's our initial temperature, and this is the temperature throughout the process, that is 288.669 Kelvin. Now let's find our final pressure. Now we know that P1 V1 by T1 is equal to P2 V2 by T2. We cancel out T1 and T2 because T1 is equal to T2. That is, initial temperature is equal to the final temperature. Therefore, we get our final pressure as 600 kilopascals into 4 meter cube divided by 2 meter cube, and that makes it 1200 kilopascals. So our final pressure is equal to 1200 kilopascals. Now, if we apply the first law to this closed process, closed system, we get du is equal to dq minus p into dv, where minus p dv is the work done. The change in internal energy is zero since the temperature initially and finally are the same. So what we have is dq is equal to p dv. We can write dpv for an is equal to p into dv plus v into dp. Now we can write this only for a constant temperature. Why? Because PV is equal to nRT, and if nRT is a constant, PV is a constant. We know that since PV is a constant, since nRT they are all constants, dPV is equal to 0, and we get P into dV plus V into dP. 0 is equal to P into dV plus V into dP. So we can write P into dV as minus V into dP, and we can replace this in our above equation, and we can write dq as minus V into dP. I did this because we know the initial and final pressures. Let's integrate this from 1 to 2, P1 to P2. So on the LHS we get the heat, and on the RHS we can further do some mathematical operations, that is, write V as N R T over P dP, P1 to P2. Therefore, Q is going to be minus N R integral dP over P. T should also be out, P1 to P2. Or we get Q is equal to minus N into R into T log natural after integrating this quantity P2 by P1. So this is going to be the heat given to the process. Now let's go ahead and calculate it. So Q is going to be minus 1 kilomole. R is 8.314 into temperature is to start with 288.669 kelvins into, let's multiply by the log natural of the pressure ratios. So that's going to be equal to start with 600, and the final pressure is 1200. So the value of Q that we get is, let's calculate it. First we calculate minus 1 into 8.314 into 288.669. So we get this as minus 2399.99 into ln of 2. So we get Q as, and we multiply this with ln. Okay, let's clear it off. So ln, okay, once again I've just made a mistake. So let's take that 2 and ln and multiply it by 2399.99. So we get it as minus 1663.54 kilo joules. Now, as we can see here, the heat is negative. It is negative because as we compress, the gas gets heated up. But to maintain the temperature, in order to maintain the temperature, we have to remove heat. And since we are removing heat from the system, its quantity is negative. Now, obviously, for an isothermal process, the heat given and the work done are equal but opposite in sign. So the work done is going to be equal to 1663.54 kilojoules. So that was all, guys, about this problem. I hope this has been an problem that has clarified your concepts about how to solve problems on an isothermal process for an ideal gas. If you have any interesting problem in mind in chemical engineering thermodynamics, do write to me. I'll make a video and put up the solutions. Goodbye, guys. Have a great time. Have a great day.